Hello viewers, good evening. You are welcome to another exclusive video on our channel, Preset Designer. It is as usual, I'm joined Abatunde Kukwala all the way from Nigeria, tutoring you today on how to use Aspen HYSYS line sizing manager to size and design process line from our simulation with Aspen HYSYS. Today I brought I'm using a simulation of a combined cycle power plant process that actually used, what's the name of the fuel? It's used pure methane as a fuel for generating electricity by generating superheated steam to drive the shaft of a electric generator or turbine that will drive a shaft of electric generator. So we have two turbines. We have a gas turbine and a steam turbine that are interconnected, you understand? So and the gas turbine produces 64.67 megawatts of power, and the steam turbine produces 7.125 megawatts. And you have a compressor that is using 57.06. So you subtract this from this, you get the power. So the net power from the gas turbine is around 10, and this one is 7. So and let me just run you through the process before I start the main D of this video tutorial. So we have airstream and a fuel stream. The airstream is compressed from ambient pressure of 1 atmospheric pressure to 15.220. I think the compression ratio for the compressor is 6 to be 15 bar. So and so therefore you have the compressed air that is mixed with compressed fuel, and there is a combustion reaction that is modeled with a combustion reactor. So this way you generate the energy for the thermal energy required for driving the shaft of the turbine, and the turbine is also connected with the gas turbine, so it's integrated to it, so you produce a net power. So then you have the exhaust, which is the hot stream that is coming at 550 degrees Celsius, is used for the heat recovery steam generator in the steam boiler. This is the steam boiler, the 3 heat exchanger is the steam boiler. So we have the different section for the steam boiler. We have the superheater heating section, we have the convective for the the evaporative, you can call it evaporative, to evaporate the steam. So this is just to superheat the steam to the very high temperature, you understand? And we have the economizer for preheating the feed water. So this is where the gas turbine cycle, the breathing cycle for the gas turbine end, while the steam turbine Rankine cycle started with we have the condensate, which is after coming from the condenser, it is pumped at high pressure to 50 bar, you understand? And I think it's also based on the compression ratio. Okay, it's not based on this is pressure ratio of 7.507, so it is compressed to 50.30 bar. Then it is returned to the economizer for preheating with the exhaust, because you can see this exhaust from the gas turbine going this 1F going to 2F, then you have the 3F, then you have the 4F. So this exhaust from the gas turbine, the one with the lowest temperature, which is 266.5, then it goes to the steam drum. Then from the steam drum, it is mixed with another stream, that is stream 11, that is coming from the convective section, because convective section is from the bottom. It is the stream that is coming from the bottom, because it is still 11A, you understand, because it is does not be vaporized, it is still liquid form. can see the vapor fraction is a liquid form at this state. Then it comes down, it's some of the heat, it exhausts some of the heat with the 11C, you understand, to produce a saturated steam, you understand. So and it heat up a little bit to 261, so you can see 243 to 261. Then it goes to the convective section, then increase the temperature to 261, you understand, 261 again. To that convection is for, because this is actually, it will supply the latent heat of vaporization to the water to heat it, to change the phase from liquid to vapor phase. So, and it's going to be in vapor phase, saturated vapor, after leaving the convective section or the evaporative section. Then it goes to the steam turbine, then produce another saturated steam that goes to the superheater for superheating, and this is the superheated steam that's coming from here. So, and we have 463.1 Celsius for the temperature of the superheated steam, and it is high pressure and high temperature, so it can use the energy to drive the turbine, and you are generating 7.125 additional power from the steam turbine. Then you have a condensate here, but it's actually using a steam, like the temperature is actually a steam, although it's supposed to be mixed phase, like there should be some vapor from vapor steam in the condensate mixture, but maybe because the thermodynamic is not 100% correct, so we are having it is in the saturated vapor state. So, and so then you have a condenser to condense the steam to fully liquid at 163.0 degrees Celsius and the pressure of 6.7 bar, and the cycle continues. So our work okay, before I explain our work, the model is actually okay, no problem. Our work today is to size the lines of the steam lines, to use to recommend a certain size of pipeline that will be sufficient to deliver the line, that where there will be no slug flow, there is no creep flow, the piping pressure drop will be sufficient, and there will be no problem. So, and as a process engineer, you are tasked with the duty of designing pipeline that will be sufficient for the process that you design. So each line that you see on the flow sheet, they represent a flow stream from one unit to another. So you should be able to design a certain diameter for the process line that will be sufficient for the line, for the flow of the line. So, and the tool that we use in Aspen HYSYS after successfully simulating your process, so we use the tool that we call is an equipment design over here in the analysis tab area of the home tab of the ribbon. So you go to line sizing. So the line sizing manager in version 9 of Aspen HYSYS, there is a like obsolete old tool that they call pipe sizing manager. So when you are you're upgrading to the newer version from version 10 upward, it will update it into a line sizing manager tool that you can use to size your lines. So, and in the line sizing manager, you have the lines, where you append the lines. You have the settings where you define the sizing criteria, that is what should be what the rules that you should use in sizing, in choosing the minimum diameter, because the minimum diameter is what you need. You need to design a very big line for a process that doesn't require but you have to ensure safety concern, that is the velocity is not too high, so to prevent erosion of the line. Because if the velocity is too high, then for a certain process, then there will be erosion, there will be problem with the line. You have to replace the piping every time, and the cost of operating, the maintenance cost will be very high. Then you have the density to the rho v, that is the density of each line should be able to withstand the vibration, you understand, so that there will be no what they call mechanical stress on the pipelines so that there will be no vibration or sound or noise or something. Then the pressure gradient too, the pressure drop should be sufficiently small, you understand. So this is the criteria that is going to use, and this is the method for the flow calculation for the two-phase system. If it is a one-phase system, it's going to use like DC pressure drop calculation correlation, using the Reynolds number for the calculation of the pressure drop with a single phase. So if it's like a two-phase stream, that's when it's going to use this method that you have, the Gregory, the Aziz, the Modane. So, and the first thing I'm going to do is to define criteria based on each of these stream, because I have different kind of stream, and you have a saturated steam, which is, for example, the 6D, and saturated liquid that is going to a pump. There is a pump, or is a gravity flow from the steam drum to the pump, and you have the pump discharge stream too, and you have the superheated steam that is going to the turbine, and the condensate, or let's just say saturated steam too, that is coming from the turbine exhaust. And you have the pump. This also is going to the pump, and this is the exhaust of the pump. And I'm not going to size the gas turbine system. It's just the steam turbine system that I'm going to size. So in this study, so I'm going to define some criteria based on this. So the first criteria that I'm going to define is for the superheated steam. So I'm going to call this superheated steam. Superheated steam. So then you have new one. So this one is saturated steam. And steam condensate, and pump discharge, and gravity flow, give me a second, flow to pump suction, gravity flow to pump section. So I'm going to define the maximum pressure gradient per length, pressure drop per length, that's pressure gradient. You have the maximum velocity and the maximum rho. So I'm using this correlation from these people person, and so I have I think it's on page 11, so I just skip to the page to make it faster. So for example, you have these guidelines for allowable pressure drop, and the limit is increased. The velocity should be kept below 170. So it should be below this if this limit is increased. So for example, we are going to just use the general one, the generic one. So for example, the superheated is greater than 200 psig. So the pressure drop is 0.012 psi per 100 feet. So I'm just going to write it over here. So we have 0.000 because it's per 100 feet. So, and this one is in per feet. So I'm going to write it 1, 2. Then we have psi by 100 per feet. So, and the maximum velocity is 200 feet per inch. That's 200. Then we have the second one. The second one is saturated steam, which is this 0.02170. So I'm just going to do it fast. So we have 0.0002 170. Then the third one is steam condensate. For steam condensate is on the is condensing steam combined exhaust. So it is based on 20, then rho v raised to power 0.2. Rho v raised to power 0.2, and rho v should be square root of rho v. So in for flow per second. So, and you look for the steam. I'm going to look for that stream. So this is the steam condensate. I'm going to look for the minimum density. So because it's a manual something. So the minimum density is this. So we have 0.1923. So when you find the square root of 0.1923, you are going to get okay. You are going to get 0.43852. Then you divide that, 20 divided by the value. So that's 45.6079 or 45 point. Get the answer to be okay. 45.60792.917. So that's the value. So, and for the pressure gradient, then we can just use the one for the saturated steam, because the stream is also very close to the saturated steam value. So we're going to use the one for the saturated stream for the pressure gradient, the value for the saturated stream for the pressure gradient. So then we have the pump discharge. The pump discharge is, I think, is up here. So you have this liquid. Okay, so for the pump discharge, we have 4 psi 11.7. So this one is going to be 0.0004 no 0.04 so 11.7. Then the next one is gravity flow to pump suction. So this is 0.035 psi, and we use this for the maximum velocity. The maximum velocity is not really very important, but it's just the pressure drop that is very important to prevent vaporization before because of vaporization in the suction line, there will be cavity formation in the impeller. So you just have this pressure 0.035 0.0035. Okay, let me confirm this a little bit. This 4 psi, so it's supposed to be 0.04. okay, this 0.04. So this is 0.0035. So this is 2.5. I took the average of the value. So this is average of this. This is 4 psi 0.035. okay. The discharge is the pressure drop can be very high in the discharge, but not in the suction of the pipe. So we have the criteria set up. So then the next thing is to append the lines that we want to pick from the simulation flow sheets. So for example, I'm going to have the list of the line. For example, we have 7C, pick them one by one. 10B, 11A, 6E, 6F, 11C, 6D, 6A, 7B. So you have these lines picked up one by one. So although everything is calculating for criteria 1, so I have to just adjust the criteria and the piping material to choose the right value. You can see this is the stream name. This is the, although there are two methods that you can use. We have the design and the rating method. Design is when you want to calculate the piping diameter. That's what we want to do. The nominal diameter, the inside and outside diameter. Then you choose the schedule, that is the pipe type that you are using, the pipe type, the thickness, you understand, and the pipe material that you are using. Then to calculate the diameter and the, if it meets the pressure drop criteria or the velocity criteria. You know, if the higher the diameter, the lower the velocity, you understand. So because the volumetric flow rate is constant, so you have to get the right diameter so that you get the right velocity. The velocity is not too much or too low, you understand. You know, if velocity is too low for a solid fluid, there will be deposits, there will be fouling, for example, in heat exchanger or something. So you have to consider for everything. So this is just the preliminary study for line sizing. So you have more detailed work to do, and you have to take into consideration a lot of factors, like a lot of scenarios, in order to get a very good line size that will be good and sufficient for a long period of time. So, and we have the criteria. I'm going to say the criteria and the criterion that will be used for each line, and the piping material that will be used for each line. So for example, this is carbon steel, because it's operating at low pressure and low temperature. So those that are operating at high pressure and high temperature are going to be using stainless steel for durability and stuff like that. So, and okay, so this is based on criteria 5, because it is 7C, that is the suction. It's based on the discharge from the pump. So this is carbon steel 2, is also based on criteria 4. I'm going to use criteria 4 for this. 10B, you can see 10B is actually 10C. 10B is suction. Then 11A is there. 7C is criteria 4, that is 5, that is reactive flow. This is discharge. 11A is criteria 4, discharge, water. Then we have 6E, criteria 5, so it's going to the circulating pump. Then we have 6F, criteria 4, discharge. Then we have 11C, criteria 2, saturated steam. 6D, criteria 2 for 6D. Then 6A, superheated steam, criteria 1, and 7B, condensing steam, criteria 3. Criteria 3 for 7B. So you see the right diameter is chosen, although I'm going to change this to a feed unit so that you can see it in inches. And I'm going to change the piping material. So for the first 5 one is 1, 2, 3, 4, 5. It's actually carbon steel. Then let me see it again. Okay, you have 3 stainless steel for high pressure. 6A. It's failing because it couldn't, maybe the schedule is very high, so it's not calculating. The piping type, the schedule SCH numbers is very high, so is not calculating. So I'm using the stainless 5S stainless steel for the piping schedule. So you have the criteria velocity, you have the rho v value, and all the criteria has been made. That's why you have the green arrow here. So, and for example, if I want it in inches, I'll go to the home tab and change the unit to feet. So it will give me the right unit for the piping diameter. So for example, you have the piping diameter here in inch. So you have 4 inch, 4 inch, 11 inch, 22, 30, 32 inch. Then you have 8 inch, 4, 4, 10, 10. So that's the diameter calculated for using the scenario of lines and velocity. So, and for the piping, you can, if you know the pipe length, you can calculate pressure drop for each of the line. For example, if I know this one to be 10, but this is just the starting calculation. For example, if you are working with you want to do analysis, like to know the pressure drop, so that you can easily fit the pressure drop in the lines and get like the real value for the lines. You do just a preliminary study. So for when you calculate the pressure drop pipeline, then you can calculate the pressure drop. And if you have like a fitting that you want that is on the line, you can calculate the pressure drop through that fitting. For if you know the fitting factor, although there are some database fitting that is in the Aspen HYSYS that you can use. For example, you can add a fitting such as pipe, you can add a cork, you can have a T, you can add a switch corner or something. You can have a water meter, you can have a gate valve. So for example, I'm going to use a gate valve that is opened. So this is the fitting. The equivalent length of each of the straight valve is calculated based on this. So, or you can put additional equivalent length that you can for all the fittings. So it's not going to use this again. You understand? So it's going to add to the fitting equivalent length. You have this here. So it's going to add to the total pipe length and calculate pressure drop throughout the pipe for the pipe. So you can use this for all the lines to calculate the pressure drop. You understand? So when the pressure drop is too high, you know how to adjust the diameter and any other kind of things that you want to do for the line to get a very good result that is acceptable. So, and you have the details. You can see the details of all the line sizing that you have been doing in this tab. So you have the details here that you can copy and print. You can select, or I think you can select or and copy it and print it. You understand? So you have the equipment that is coming from and the equipment that is leaving. You have the piping material, the density. So these are how to use the line sizing manager with Aspen HYSYS. So in case you want to do the line sizing more rigorously, because it's not just one tool that you can use for designing line sizing in Aspen HYSYS. You can use some unit operation. For example, you want to model the pressure drop in the flow sheet itself, because analysis is just you are trying to analyze the result of your simulation, so as to make it faster, to make the simulation like it's different from the simulation flow sheet calculation itself. So but if you want to incorporate the line sizing with the simulation flow sheet calculation, you can add a pipe segments in the flow sheets, and you can find the pipe segments in the model palette, and you go to the piping and hydraulics section of the model palette. So you have mixer, you have a T to model a T or mixer, but you don't really need to do that. For this one is just general unit operation. So this is a pipe segment that you can use for separating it line. So you are going to divide the line into two. For example, for lines 5, I can copy line 5 over here for this 5A, 6A over here, and paste it here. So I'm going to write 6A to and this I'm going to write 6A3. So if there is energy stream, I'm going to put the energy stream. I don't think energy stream is required. Okay, require energy stream Q6A. So the heat loss through the heat stage. So then I'm going to use like the same method of flow correlation calculation for the pressure drop calculation and the rest. We have the theta P, we have the duty that is calculated, and this is the pressure drop that's calculated to the line. So it's going to export the pressure drop, like calculate it to calculate the outlet pressure through of the line. So you know the required pressure that will deliver to the line. So that's like the flow assurance something. So then you can rate the design by going to section like what you have done, so and specify the pressure that the line sizing you have specified for it. I think the line sizing is short for something. Let me confirm from the analysis. 10 stream 6A, so it's 30 inch, so and stainless steel. So I'm going to pick 30 inch and stainless steel. So I'm going to put it's not going to be actual, so it's going to be schedule 5S. So I want to put 30 inch. So that's for the piping. So from here it's going to calculate the pipe length. So let me say 10 inch, 10 feet. So for the heat transfer, I'm going to pick 0 heat loss. So saying not enough information. Okay, saying not okay. Oh, I think the reason is because the stream is not fully defined. This is 2A, so I'm going to define it to be based on this is a stream. So I have this is a stream. So okay, so it has calculated the pressure drop. So I think the pressure drop is not important. So the pressure drop is very small. You have the energy drop, and so apart from this, you can still check the parameters like the default value for the tolerance and the for heat flow calculation, temperature, pressure tolerance, and for the emulsion like the viscosity, like when there is two liquid phase or something. So then you have the rating where I specify the pipe segment that you have, the heat transfer loss. You can put detail or any kind of things. So that's it. So this is the worksheet, and this is the performance and the insulation. So this is the rigorous model is actually done using rating approach, you understand, apart from the design approach in the analysis. So you can do some flow assurance analysis too, like if there is a CO2 emission, if there is an erosion in the piping, if there is hydrate formation, there is slug flow or wax deposition. For example, if you are working with like asphalting or asphalt modeling, there is a very viscous liquid, so you can do those kind of analysis on the pipeline in Aspen HYSYS. So and to do the rating analysis, so before I finish, you just use this tab and click on rating, so you can specify the diameter that you want to use. So for example, I'm using 4 inch, so if I pick 2.5 inch, it's going to tell me that the criteria failed, you understand. So I can choose the right diameter that will be sufficient for the criteria to be met, and you have that. So apart from the pipeline, you can use other approach in the other unit operation in the pallets for the same section. You can use a gas pipeline if you are modeling a gas line, or you can use hydraulic soft flow sheets for like offshore, like upstream section, like when you are modeling like oil flow from upstream, or you want to do a rigorous calculation for hydraulic calculation or flow assurance in the process production, like oil and gas production plants. So you can do that. So that will be all on this tutorial. So I hope you are able to understand the concept of what we are trying to explain, like how to do flow assurance, line sizing, process line sizing with Aspen HYSYS. And I hope you understand the concept and combined cycle power plants simulation and how to design line for those systems. You can use guidelines from API like or you read textbooks on the heuristic of sizing process line. There are different scenarios and different conditions, like different factors that you consider in designing. So you look for the limiting factor in designing the pipeline. So thank you for your time.